Hi, my name is Chuck Cimino, and I'm a Senior Director of Product Management here at Lakeshore Cryotronics. Today, I'm going to do a demonstration and overview of our model M81 synchronous source measure system. The M81 system is comprised of the control instrument in front of me and these four modules next to me. These modules are comprised of a differential or balanced current source module, a single or differential voltage measurement module, a single-ended current measurement module, and a single-ended voltage source module. These four modules, in combination with the mainframe, can be combined for up to 3 source and measure channels simultaneously synchronized for an all-in-one complete source and measure solution. The M81 system is the most recent member of Lakeshore's measure-ready instrument line. As such, it uses the same packaging as our other instruments in the measure-ready line, a nice, clean, simple touchscreen interface, and easy-to-use control panel for each of the modules, and a nice compact half-rack package. The rear of the instrument contains standard IEEE 488 LAN and USB remote interfaces, interface connections to our modules, our analog amplifier modules, and some internal and external reference and monitor connections. Some things that are unique about the M81 system are its sampling architecture. Unlike many systems with multiple channels of capability, this is not a scanned system. Rather, all source and measure channels are simultaneously sampled at a very high rate, providing DC to 100 kilohertz operation, including lock-in operation on any channels up to 3 source and 3 measure simultaneously. This ensures very time-correlated synchronous measurement using our Measure Sync technology. Now let's take a little deeper look at each of the modules. So let's talk a little more about the M81's analog amplifier source and measure modules. The first module I'd like to talk about is our balanced current source module. This has 2 separate connections that are triax and guarded for very fast, low current, low noise performance. Also our common mode rejection technology that can eliminate the effects of imbalanced wiring in many large installation applications. This source is programmable in both frequency and amplitude, DC and AC, and can be used in combination with the next module I'll talk about, our voltmeter module. Our VM10 module you can think of as our lock-in module. This module can measure DC, AC, and lock-in signals generated by our BCS or any other source module. Single-ended or differential capability, differential being important for rejecting ambient noise. Also included in our voltmeter module is user-settable hardware and high-pass and low-pass filters. The system also supports a number of digital filters in combination with the hardware filters to optimize signal-to-noise performance. The third module I'll talk about is our VS10, our voltage source module. This module is for applications that prefer a constant voltage rather than a constant current, as in the BCS module. This module also has noise optimizations. There's some intellectual property associated with this module that allows us to mix DC and AC signals without compromising resolution. For example, a small AC signal on top of a larger or varying DC signal. And the final module that is often used in combination with one or more of the other modules is our current measurement module. This is known as a feedback ammeter. This is also capable of DC and AC and lock-in detection. Also has filtering built in and covers a wide range of amplitude signals that can be generated by our other sources and can track your device performance. More modules are in development on the way. We'll talk about those in future videos. One thing common to the M81 system and all modules is the inclusion of a standard 2-meter long high-level cable that we'll talk about shortly that connects each module to the instrument. This cable is a noise immune signal path and provides up to a total of 6 meters between any amplifier module and the instrument mainframe. Standard is 2 meters, the cables that are all attached here. We sell an optional extender that's 4 meters. Some very large installations can benefit from having the modules very close to the sample with the shortest possible low-level wiring to minimize noise pickup and other unwanted phenomenon. So the M81 is a modular system, but it's also a physically distributed system in that way. Okay, now that we've covered the M81 mainframe and the 4 amplifier modules as an overall concept, I'd like to set up and make some measurements and show you the instrument in operation. I'm going to use this available demonstration kit that we have. Comes with a little test box, we call it, that provides some easy connections to a number of sample cards. Here we have a selection of sample cards, socket boards, low value resistances, high value resistances, some optical tests, and here we have just a selectable resistance. We'll get into some details. First up, I'll wire up our current source and our voltmeter in a Kelvin connection, and we'll just make some resistance measurements to show you the features and settings of the M81. All right, step 1, I select my balanced current source module, set it next to my test device, and take the LEMO connector that comes built onto the module and plug it into one of the 3 source ports on the rear of the instrument. I'll take my voltmeter module, do the same thing. I'll connect it to one of our 3 measure ports on the rear of the M81 instrument. The next step is to tell the instrument the modules need to be loaded. Come to the front panel of the instrument and I'll hit load. And now actually you can see measurements are being made on the voltmeter module. Next step, I take some simple BNC cables, connect them to the voltmeter inputs, and then I connect them to my sense points on my sample box. Voltmeter is connected. I now need to connect my current source via the guarded triax connections. I'll connect these in a Kelvin configuration to these outer terminals, and I'll connect these to the plus and minus current output of the BCS. So now that we've got our test setup comprised of a current source, voltmeter, and a Kelvin connection to our test box with a resistor, a variable resistor, set to 1 megohm, I'm applying 1 microamp and I'm measuring 1 volt through 1 megohm. And I can see it as a voltage. A typical display is a voltage or a current, or I can convert that to a resistance and I see my 1 megohm value. It's a DC measurement. There are limits to how low I can go at a given current. I'm at a microamp. If I start to drop my resistance value, 100K ohms, you see the value change to just under 100K. 10K, see the value dropping. 1K, the voltage I'm measuring is very, very small and it's a DC voltage. And soon you'll see I don't have the accuracy that I had at higher resistances. We'll talk about using an AC technique, using a lock-in detection method to get around some of the problems of a DC technique in terms of offsets and other phenomena. And I can continue down until I get to 1 ohm. Now 1 ohm and 1 microamp is 1 microvolt. So I'm measuring now 3 ohms instead of what I should be measuring is 1 ohm because I have some offset voltages that are interfering with my signal. A way around that is to do reversals or to do AC lock-in technique. We'll talk about the AC lock-in technique, and I'll change the configuration to show that. Okay, so now I changed my setup from a DC method to an AC lock-in method. I'm still putting out a microamp of current. I'm at 100 hertz, and I'm using AC lock-in detection to measure my 1 ohm value. Previously, I was measuring about 3 ohms in this resistance display, and now you can see I'm much closer to the true value of 1 ohm set by my resistor box here. If I prefer, I can get out of resistance mode and I can go to a more traditional lock-in, where I can see X and Y or polar voltage signals. But for simple resistance, I can put in an easy, convenient V over I mode and look at resistance. And as I now increase this 10 times, you'll see the resistance value go up by 10, and I can actually go below 1 ohm to 1/10 of an ohm. And even though I'm only sourcing a microamp, I should be able to see about 1/10 of an ohm once the filtering is settled. We'll go back to the 1 ohm setting, measuring basically a microvolt using a lock-in technique. So this demonstration was very simple, using a basic resistance to show the power of our M81 system, the simplicity at setting up a differential current source voltage measure, Kelvin resistance measurement, some basic settings on the front panel to show you resistance or lock-in detection or voltage and current. Of course, the other 2 modules can be set up in a similar fashion to source voltage, measure current, in any combination up to 3 sources and 3 measures. Right now we're just doing 1 source, 1 measure. We could easily have 3 sets of these with 3 independent samples. Further down on every module's control panel are many advanced settings. We'll get into those in future videos and talk some more complex applications with some more sophisticated samples. But this is just a quick demonstration of how quickly and how easily I can set up and really be making very, very low level measurements of microvolts in the tens and hundreds of nanovolts, kind of in the open air with a couple of modules and the M81's different approach, a new concept for low-level, high-precision measurements. If you need more information, feel free to contact sales@lakeshore.com. You can visit our website. We have a page on our M81 synchronous system. You can look at our data sheets, a series of app notes and white papers. We have a growing body of reference material there, and we certainly have application scientists that are happy to talk to you about more complex applications and things you might want to specifically use the M81 for. Thank you very much.